In an earlier lab, you measured the transient response of the RC circuit. In other words, when you put a step function on the input, right, what happens at the output, and you saw the capacitor charged up. Then you did the CR circuit, which is really just the transposed RC circuit, and you got a differentiator type of thing where put in a step and you get an exponential rise and a decay back down to zero. So we could also analyze these circuits in the frequency domain. So frequency domain is assuming that nothing is really changing much. In other words, the frequency isn't changing. Things are in what they call a steady state. So that's the advantage for the frequency domain, is it's good at measuring things in the steady state. The time domain is good at measuring things in transient conditions, and that's why we do things like step function and impulse response measurements when we're caring about those things. So this is our basic RC circuit from one of the earlier labs, where you have a function generator feeding a resistor, and then that's connected to a capacitor. You have an output going to an oscilloscope. Your grounds are tied together. Remember, the black wires are always ground. And then, so if we go over here and look at our instruments, so there's our function generator, our wire going to our breadboard. Then we have a T. Second wire is going to channel 1 on the scope, the yellow channel. And I have my waveforms visible there on the scope. So the yellow is the input, and then the blue is the output. In other words, the blue is the output across the capacitor, this lead, and then the red, the blue waveform. In other words, the waveform here is the output on this lead, and then this lead is the yellow waveform. And they're both sinusoidal signals, and they're 30 hertz right now. And I also put on a spectrogram measurement. You can see this little purple dot right here, or that little impulse, right? That's telling me that, yes, you're seeing a sine wave, and it has 30 hertz of frequency content. And if I change the frequency, like if I go over here and change the frequency, now as I'm doing that, if I look at the oscilloscope, so you can see as I'm moving up in frequency, the period's getting smaller, and those impulses are going to the right, meaning that they're higher frequencies. So also notice as I did that, the sine wave on the output, the blue one, shrunk. So I'm going back down in frequency. You can see the impulses going back to the left. So I'm down around 10 hertz right now. So the impulse is right up against there, the frequency response measurement. And these are very low frequency waves, and they look almost identical. And as I step the frequency up, so it's 20 hertz, 30 hertz, 40, 50. Now it's starting to be noticeable that you can see the amplitude of the voltage across the capacitor is decreasing. And also, if you look at the height of that spectrum right there, it's also decreasing. So you have to wait till it stabilizes. So we're at 100 hertz. Now I'm going to go to 200 hertz. They call this log step, 300 hertz. And you can see, the blue waveform's getting smaller and smaller, and the corresponding magnitude in the frequency domain is getting smaller, whereas in the frequency, or the magnitude of the input, is staying the same because that's not changing. So now, in order to really look closer, I have to change my horizontal scale there. So now I'm on a smaller scale, so I'm at 600 hertz at 1,000 hertz. And then so if we go over here, so I was moving in 100 hertz increments there. Now, if I get to 1,000, I might want to go and switch over. So now I'm going in 1,000 hertz increments. And so this is what we call a log type of progression. It will get to 10 kilohertz. And then I'll move over again. Now I'm going in 10 kilohertz progressions. Now, if I go back over to the scope, you can see that the signals, basically there's virtually no AC signal whatsoever left on the output, because it's attenuated into the noise. You can see there's a little bit of noise down in there, and the signal is so small we just can't see it. Whereas the input waveform is staying the same. So I'll go back down in frequency, and now I need to switch over to a smaller number. I change the horizontal on the scope, and you can see there a little blip starting to appear, and we're also starting to see a little bit of sinusoidal action on the blue channel on the output. Let's go to lower frequencies. So what we're doing right here is they call a sinusoidal sweep. So we're sweeping the frequencies, going from low to high or high to low, and looking at how the magnitude of the output changes. And so what you're going to do in this lab is that very thing. So you're going to choose a cutoff frequency for your filter. So the frequency is going to be 1 divided by 2 pi times R times C, or that's in ohms and in farads. Make sure you get that right. So you're going to choose a time constant according to some specs. Then you're going to connect it up to your instruments. You're going to do a sine sweep, where you're going to say get maybe 10 or 15 points. You'd say make a measurement at 10 hertz, figure out what the magnitude for both waveforms is. Go to 20 hertz, go back and make a measurement, etc., until you don't really see any signal. That's why you want to go in fairly large steps, because otherwise you'll be in the lab all day. That's where that whole logarithmic spacing thing comes in. So you can see now, I quickly made it to 1,000. Signal is very small. So note, when the signal is very small, you might have to change the scale, the vertical scale on the oscilloscope, so that you could see it. Like, don't just leave it on the setting for the large amplitude, otherwise you're going to be missing out on information. So you could see I'm adjusting my knobs over here, adjusting my vertical and horizontal. So even though that looks similar in size there, the volts per division is 10 times smaller on channel 2 than it is on channel 1. So make sure you use your scales appropriately. Now if we go up to say 10 kilohertz, it's getting smaller yet, but there's still signal there, and that's still measurable. It's just getting very small. So use your scope appropriately, take some measurements. Okay, so you saw how you do a frequency sweep with the instruments. Connect your function generator to your circuit, you dial in a certain frequency, you measure the V out and the V in amplitude. So typically you'd make some kind of chart, maybe put it in a spreadsheet. So you have your frequency, V in into your circuit, and then V out. And then you might, depending on what your corner frequency is, and remember for the low pass and the high pass filter, the first order passive filters, we call it FC, frequency cutoff, equals 1 over 2 pi times RC. And remember, these are in ohms and farads, not microfarads and kilo ohms or something. So you just want to make sure you get those units correct. So say if our frequency was arbitrarily, 10 hertz, just for easy math. So we want to take a frequency sweep that encompasses that range and maybe goes a decade above and below, a decade or two above and below, because that'll kind of show us the pass band and also the cutoff. So here, maybe if we're at 10 hertz, maybe we'd start, just because it would be really hard going much lower, at like 0.5 hertz or 1/2 of a hertz. And then we measure input signal as 1 volt in magnitude, or output's 1 volt in magnitude. And then we're going to 1 hertz, we're at 1, and maybe we do a 2, and then a 5 and a 10. So this is what like a logarithmic type of progression right here. So 10 hertz, then a 20, 50, 100. And then, so now we're kind of past our cutoff frequency once we get to 100. So maybe we go to 1,000 hertz, 10,000 hertz, maybe 20,000 hertz if we really want to get an extra point. So these should all stay the same. They're all 1 over there. But as we expect, if our cutoff frequency, if this was a low pass filter, right, passing the low, blocking the high, we expect to start losing output once we get into the vicinity of 10 hertz. So I'll just pretend right here, maybe that's 0.8, 0.7, 0.6, blah, blah, blah. It gets 0.001 or something as we get to the really high frequencies. So now we'd plot this, and we'd do a plot of the magnitude of V out over V in, which is what I drew right here. So magnitude is almost the same way as saying amplitude is going to be on your vertical axis, and your horizontal axis is going to be frequency. So, we're starting at, say, 0.5 hertz, and you want to make this a log scale down there. So that axis is a log scale. And actually, if you make this axis a log scale, so if you have a log-log plot, then this will be a little bit easier to look at, because these equations kind of relate to power. And so so we're at 0.5, V out over V in equals 1, right? It's kind of 1 for a while. Then we get to about our cutoff frequency of 10 hertz, right? We're going to start to see a decrease, like an attenuation, and it's going to go down as we go up to our frequencies. That might be 100 hertz. Once again, we're on log, not kilohertz over there. So you'd see something like this, and this is what we call our magnitude transfer function. So an interesting thing to note is that the magnitude at the cutoff frequency should be 0.707. And so that comes because of the power. So that's actually the half power point. That means when you're at 1/2 of the full bandwidth power, so it's 0.707 or 1 over the square root of 2. So you're going to make a graph like this for your low pass filter. So you're going to make another one for your high pass filter, where the high pass filter has the same cutoff frequency, but you're going to see something that looks more like that. So those are the two things that we want, or those two plots, low pass filter and a high pass filter. Make sure all your axes are labeled, and then you're good to go.